So we've used some of this terminology already, but just to go over it with our polynomial functions. So this is a bit messy, but it's that we have numerical coefficients and an exponent, and as we add up those terms together, it creates a polynomial function. So we have these real numbers as our numerical coefficients. Our leading term is the term that has our largest exponent, and that's going to determine the long-run behavior of our function. So that should look familiar as our power function. So some different forms that we'll see is when it's a parabola opening upwards or downwards, or increasing or decreasing in terms of long-run behavior. We'll get that from the leading term. And then the degree of the polynomial comes from that exponent on the leading term. So let's talk about how we can determine that long-run behavior, finding that leading term, and going from there. So with this first function, what I go and do is look for the largest exponent, and that's going to be my leading term. So I'm looking at an x cubed there. And what that tells me is, so that's an odd degree and has a positive out front. So I can remember my x cubed power function looks something like this, and that's going to be the same long-run behavior for this polynomial. In the middle here, all sorts of things can be going on. We're going to talk about that with the short-run behavior, but in terms of long-run behavior, so as x approaches negative infinity, as x approaches positive infinity, what we can get is that as we go to the left, our function should be going down, so to negative infinity. And when we go to the right, our function should be going up off to positive infinity. With this function here where it's all factored, what we can do is figure out the leading term by multiplying all of our x values. So we have negative 2x, x, and x. So multiplying those, our leading term would be negative 2 times 1, 2, 3, 4, 5 x values. So I have an odd degree, so that makes it similar to the last one, but with the negative out front, it flips it so that it would be decreasing like this. So what's going to change is how we work with infinity. So as x goes to negative infinity, so as we go to the left, now we're going up to positive infinity. And as we go to the right, our function is going down towards negative infinity. All right, looking for our largest exponent is going to come from that exponent of 4. So we have an even power, an even degree, and a negative out front. So that's going to be shaped like our downward opening parabola. So as x goes to negative infinity, our function's going down to negative infinity. As our function, or as x gets larger, so as we go to the right, our function also goes down over there towards negative infinity as well. And with this one, this is just a classic parabola right here, and it's opening upward. So with that, as x goes to the left, our function goes up. As x goes to the right, our function goes up. All right, so that's how we can use the leading terms to figure out our long-run behavior. Then in terms of short-run behavior, what we can think about are zeros and turning points. So zeros are where we cross the x-axis. So with each of these, we're just going to talk about the degree, the turning points, and the number of zeros. So with this first one, we have a degree 2, or really an even degree. Let's just say even or odd. So let's say even degree. Turning points, that's the green point right there. It's where we switch from increasing to decreasing or decreasing to increasing. So we have 1 turning point. And then the number of zeros, we have 2 zeros. Okay, with this one, this would be an odd degree because it looks like something cubic, even though that short run behavior is a little different. We can see our 2 turning points here, and 3 zeros. So you should start seeing is that the number of zeros is one more than the turning points. Here, in terms of the degree, what I'm looking at is we're going to positive infinity in the long run, and that tells me that it's an even degree because it's going to the same spot. And then we have 3 turning points and 4 zeros. Here, what I'm going to notice in long run behavior, down to negative infinity up to positive infinity, so that tells me it's an odd degree. We're going to have 4 turning points here and 5 zeros. Okay, so there's some properties that we can see with our different polynomials. Now let's start putting together what's happening at those zeros and the different behaviors we can see. So one of the behaviors we could see at a 0 is that when we hit that x-axis, we have a bounce. We're going to bounce off of it. And what's happening there is that at that 0, we have degree 2. We have an even degree is going to make, or sorry, not degree, multiplicity. We have a new word here. The multiplicity of that 0, which means when we're looking at our zeros in factored form, that's going to be our exponent on that 0. So that right there, that exponent, if we have one, is called a multiplicity. So this would have a multiplicity of 2. This one right here, so our 0 is right there, and we're just passing right through. And when we're passing through, this tells me that we have a multiplicity of 1. It's like it's linear right there. Whereas that last one is like it's quadratic, like having an x squared. And this is just like having an x. And then this one that flattens is like having an x cubed. So this one is where we flatten through, and this is going to have a multiplicity of 3 to make something that looks cubic at that point. So that tells us of the behavior at the zeros. So let's put this together, and we can make quick little sketches here just based on long run behavior, our leading coefficients, and the multiplicity of our zeros. So with this one, leading term will have 2x times x times x times x times x. So let's see, 1, 2, 3, 4, 5 x's. So that tells me my general shape is going to be like this, but then zeros are occurring at x equals 0, positive 1, negative 2, negative 3, positive 4. And then the multiplicity on all of those, so what I'm doing is I'm looking at the exponents, which all of those exponents are 1. So all of those have a multiplicity of 1 for all. So with that, we're just going straight through. So what I could do is just get a very, very general sketch going here. And let's go, let's see, negative 3 to positive 4. So 1, 2, 3, 4. 1, 2, 3, 4. We have zeros at 0, 1, negative 2, negative 3, positive 4. So I have those coordinates there. I know my function is going to be coming from negative infinity and going off to positive infinity, so I have an idea of what's going on in the long run. And then we're just going through all of those zeros. So what I'm going to do is start down here and then just go through, turn through, something like that for a very, very general sketch there. But not too bad, just given that little bit of information. Okay, with this one, so for the leading term, I would have an x cubed times 2x times x squared. So my leading term is going to be 2 times 3x's, 4, 5, 6. Okay, so our general shape is going to be like this. And then for our zeros, we're going to have a +1, a -5/2, and a -6. And then we are going to have some different multiplicities here. So we have a 3, a 1, and a 2. So we're going to see all of our shapes here. So we're going to flatten, we'll go through, and then we have a bounce. What I like about these is if you know that long run behavior, it should match up so you end up on the right, or rather the correct side of the axes. So let's see, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So we have a +1, a -6, and -5/2. And I'm just going to make notes to myself. So at +1, that's where we're going to flatten. At -6, that's where we're going to bounce. And we're going to go straight through at the -5/2. Okay, so we're starting at positive infinity. We bounce, we go through, and then we turn, and we flatten through. And we end up going off to positive infinity there. So we shouldn't be crossing the x-axis again there. There's a good sketch going there. Okay, last one. So with this one, our leading terms have a -3x times. We have an x squared, a 2x, and an x. So -3 times 2, so -6. And then 1, 2, 3, 4, 5 x's. So we're going to have something that does this. And then for the zeros, let's see, we'll have 11/3, a -8, a 21/2, and -12. And then for multiplicities, let's see, we have a 1, 2, 1, 1. So we just have one bounce at that -8. I'm going to do a very, very general sketch here, just for the sake of saving a bit of time. Okay, let's say we have our -12, we have our -8, we have our 11/3, we have our 21/2, and that -8 that's where we'll have a bounce, but everything else will be positive. Okay, so we're coming from positive infinity, and we're just going to go straight through, bounce, through, and down to -infinity for a very, very general sketch there. But that's quite a bit of information just given the function that we can get without any sort of graphing and really pretty minimal calculations.